Hello and welcome to this clip going through question 12 from the progress test one from September. This was one of the questions that quite a few people struggled with because it required not only quite a lot of recall from the previous summer but also some analysis of your knowledge. In fact, one of the questions tells you to apply your knowledge. So we've gone through the NMR question in class from later on in the test. And like I mentioned, we'd put this one on YouTube for people to go away and have a look at. So, first one is this one here, benzoic acid. You might remember we did benzoic acid back in July as one of our core practicals. So it was chosen specifically as one of the questions here to prompt your memory there. So it talks about how benzoic acid can be nitrated. Now we've done nitration of benzene, so there's no reason why you can't nitrate a substituted benzene ring as well. And it says it happens in the presence of concentrated sulfuric acid as the catalyst, shown in equation 17.1. So it asks you to outline the mechanism for this nitration of benzoic acid, and it asks you to show how H2SO4 behaves as a catalyst. So going down the page, just double check how many marks we get for that. We get 5 marks. So normally the mechanism is about 3 marks, and the H2SO4 behaving as a catalyst will be a mark, and you may as well put in the generation of the catalyst as well. So looking at the instructions, it tells you to show how H2SO4 behaves as a catalyst. So you'll need to show how it's used to generate the electrophile, to draw the mechanism as well, and then show how the catalyst is regenerated. So that's the equation we want, and just to clarify what the catalyst is and what the electrophile is. So when you're drawing the mechanism, you start with your aromatic species, but think carefully where the nitration site is going to be. So you can see clearly that nitration occurs at carbon number 3 on the ring. You'd expect that because the name of the compound is 3-nitrobenzoic acid. So you have to be quite careful where you put your electrophile in your mechanism. So you put your NO2 plus electrophile next to C3, and then you can put your curly arrow coming off the ring, so it touches the circle inside the ring, which represents the delocalized pi system, and it points, even touches, the nitrogen, which is the atom to which carbon 3 will bond. So be careful with the precision of your curly arrows, because if you get sloppy, you can almost imply something else that you didn't mean, as opposed to what you are trying to say. So when you draw the intermediate, be careful the way you orientate the partially delocalized pi system. It needs to be pointing, the open end with the positive charge needs to be pointing at carbon number 3. It needs to extend all the way around the other carbons. The curly arrow breaks the carbon-hydrogen bond at that position, and that means the H comes off as H+. So don't forget the H+, lots of people do, and once you've completed that, that would be about 3 marks. Okay, so moving the page down a little bit, we can do the regeneration of the catalyst. And that completes the answer for us for that one. So let's now go on to the next section. So you can see straight away in this question that it's a leveled response question. So the things you need to think about is precisely what it is you have to do. So looking at the instructions, you can see from the command words that you need to describe a method, determine the percentage yield, and check its purity. If you miss anything out, you're automatically going to start losing marks. So you can't really bluff your way through these questions. So you have to show an attempt at each of those. And obviously the more effective your attempt, the higher the marks you're going to get, and the more chance you have of getting 6 out of 6. So it's a 6-mark question, and it's 1.3 minutes per mark for an A-level paper. So that's roughly 8 marks to do this whole thing. So you can afford to do a couple of minutes of planning. So, looking at the information, you can see that the question tells you quite clearly that you're purifying a solid. So think carefully here about what type of techniques are used to purify a solid. So you can see I've taken a couple of minutes to stick something down in no particular order, but now I can actually use that to draw information from. So I'm going to put a box around it, and I'm going to use that to construct my answer. So that gets my brain thinking. It's a place to park information that your brain comes up with. Now you can process it and decide in what order I need to do everything. So thinking back to your core practical when you actually made some benzoic acid, it's not actually that different perhaps to make nitrobenzoic acid. The reaction might be slightly different, but you're still making an organic solid. So technically, the same set of steps should be used. Now it's important to just point out here, it says describe a method to obtain a pure sample. That doesn't mean what you have to do from the starting materials. Obtaining a pure sample means you start with the impure solid. So you assume you've got the impure solid, now you need to purify it. So taking all those things that I've jotted down in my plan, so you recrystallize the impure product that you've got at the beginning, then dissolve it in the minimum volume of hot solvent, cool that solution, refilter the pure solid once more, and leave it to dry. So once you've actually got your dry, pure solid, you can measure its melting point and compare this to data books. So that allows you to check the purity. But we haven't done the percentage yield yet. So even though we might be feeling quite chuffed with ourselves at this point, we have to make sure that we're actually answering what the question wants. So the question wants us to determine the percentage yield. So I've just taken a copy of the previous page's equation, so you can see that 1 mole of benzoic acid gives 1 mole of 3-nitrobenzoic acid. So you need to work out the MR of each of your compounds. What I tend to do is I convert the displayed formula into or the structure they give me into a molecular formula, so it's easy to count up and calculate the formula mass. So your relative molecular mass is 122.0 for benzoic acid, and 3-nitrobenzoic acid is 167. So what you need to do is be able to convert this into moles. So putting down the equation for percentage yield, we want the actual moles, which is pretty much the moles from your 4.85 grams of 3-nitrobenzoic acid, over the theoretical moles, which is what you would expect from 4.97 grams of benzoic acid. So let's get those moles by taking those masses and calculating it. So now we can put in those values, and that gives us 0.0290 over 0.407. So multiplying that by 100 gives us our percentage yield. And I think that ends up as 71.3%, to 3 significant figures. Okay, so I think that means we've covered the determination of the percentage yield. We've covered the purity checking, and we've covered the method. Okay, so it's now time to have a look at the next page. So on this page we've got 3 aromatic compounds, phenol, benzene and benzoic acid. And we've got some information about the conditions required to nitrate them. Phenol and benzene you'll find in your textbooks and your notes. and the things that you've worked on over the summer. Benzoic acid, we've made it, but we haven't really talked about it that much as an aromatic compound. So this is a little bit of application here. So looking closely at the conditions required for nitration, you can see it's quite easy to nitrate phenol. A little bit harder in terms of the concentration of the acid and the temperature required to nitrate to nitrate benzene. And then finally, benzoic acid is the hardest to nitrate of all. So most people would find that quite straightforward to identify the trend. But if you look at the command words in the question, it actually requires a comparative answer because it's the relative ease of nitration, not just state the trend in nitration. So it's a subtle shift in nuance there. So the way you'd say it is you'd have to mention what's the most easy to nitrate, what's the least easy to nitrate, and place the middle one in between the two. Now I've said OWTTE, meaning all words to that effect, because it doesn't mean you have to write it down in the exact way that I've done it. You could draw an arrow, for example, with phenol at one end and benzoic acid at the other, and say increasing difficulty of nitration or something along those lines. But either way, you need to make sure you've done a comparative answer to get the mark on this question. And quite a few people struggled with that because they maybe didn't spot the way it said state the trend in the relative ease of nitration. So moving the page down, it says apply your knowledge of the bonding in arenes to explain the trend in part B, I. Now your knowledge would be basically what you can remember about phenol. So if you've recalled your phenol information, you'll remember things like a lone pair of electrons from the oxygen in OH being delocalized or partially delocalized into the pi ring. This in turn increases the electron density of the pi ring, and the consequence of that is the pi ring in phenol is now more able to induce a dipole in an electrophile and therefore react more quickly. But that's just recalling your knowledge. The application of your knowledge is taking that idea and trying to link it across to benzoic acid using the trend you've just worked out. So here's where we bring in directing groups. So OH in phenol is electron donating or 2,4 directing, and that must mean if that makes it easier to nitrate, the opposite must be true for benzoic acid, so it's electron withdrawing or 3,5 directing. I've left two other words in there, activating and deactivating, because you might see those online if you look this up or look in textbooks. I'm going to talk about those two words a little bit later once I've completed the answer, because I think it's important to point out a slight limitation of using them. So popping the beginning part of the answer in, you put oxygen in phenol delocalizes the lone pair of electrons into the pi system, which increases the electron density, meaning that phenol induces a dipole in electrophiles more easily than benzene or benzoic acid. So there's two key points there made, so that gets you 2 out of the 3 marks. The third mark has to come from somehow verbalizing or expressing what we thought about at the bottom of the page in a way that gets the mark clearly. So the COOH in benzoic acid is electron withdrawing, 3,5 directing. So this reduces electron density in the pi system, making it even harder than benzene to induce a dipole. Now, I mentioned the deactivating and activating a couple of seconds ago. Although they're technically correct, if you think about it, what does deactivating or activating really mean? They're kind of a little vague. So let's think about what they're really trying to say. They're talking about the direction of the position of substitution, so is it 2,4 directing or 3,5 directing? Or you could talk about it in terms of the influence on the direction of electron movement. Do the electrons get donated into the ring? Do the electrons get withdrawn out of the ring? So my advice would be to perhaps consider not using activating or deactivating, because quite often in mark schemes it says ignore deactivating or activating, which means that although they're not wrong, they're not quite correct enough to nail the mark. So with that in mind, we'll finish off now because I think that is the end of the question. Hopefully this clip has taken you through a few bits of the recall that are required, but more specifically how to actually apply it, how to connect it to what the actual question is asking you to do. So again, thanks for listening. Until next time, see you soon.